Hi, everybody. My name is John Handler. I'm Director of Solutions Architecture at AWS, and here to present today on OpenSearch's vector search capabilities. I'm joined by...
Hi, everybody. My name is Yuye, and I am a machine learning engineer from AWS OpenSearch. I mainly work on machine learning features like vector search and agent framework. Nice to see you.
Cool. All right, thank you. All right, so I think that, I was really happy to hear Eric's talk in the keynote because it nicely brings forth this concept. Over the last 20, 25 years, we've all kind of trained ourselves to engage in this iterative process of one-shot matching, where you go to the search engine, you type in some words, you get some search results, and maybe they're the right results. And hey, if they're the right results, great. You go off, you're happy. If they're the wrong results, then you think about, like, how do I rephrase this? How do I recast this? What different words should I type so that what I'm searching for will come to the top, right? So in a lot of ways, we've been driving the semantics and meaning in search. And you can see this play out. Eric showed an example. I have an example. This is a search for hot weather hats, which presumably are hats that you would wear in hot weather, though what comes back is hats that are warm to keep you hot, right? So as opposed to kind of perhaps what you really intended were these hot weather hats, where you wear it in the sun, it keeps the sun off of you, you remain cool, right? And the difference here, as we've all known, is bringing in semantic information through large language models, creating vector embeddings, and doing searches based on vectors. So in the search world, this technology, this embedding technology, and large language models have brought a number of new paradigms for searching. So first of those is semantic. That's the example that we gave. Semantic search brings in context, where words are represented as vectors based on the surrounding words and the word itself, and it helps capture the meaning for that word. So multimodal search brings in additional information, like if I want to search for a pair of sneakers, but I want a pair of red sneakers, and I want it to look a certain way, I can add an image and search based on the image and also text. Sparse search is a different kind of embedding that brings in both lexical through a tokenization scheme and semantic through weighting those tokens, and we'll see how that plays out. And then finally, to Eric's point, we have more of a conversational model, which breaks out of that one-shot, run a single query, think about it, redo the query. With conversational, we bring in the conversational context to spread across multiple queries and bring back results that are relevant within that context. Nope. Okay, so we can do all of this in OpenSearch, and there are various mechanisms and ways, and connecting all the pieces and building actual conversational or multimodal or hybrid can be a little bit complex. So what we're talking about today, first of all, is what are the different kinds of searches, and second of all, we've open sourced an example library and a management library that helps you build all of this. So in the first part of the talk, I'm going to go through what are the kinds of search. Second part, Yuye is going to demo and show you what we've built that hopefully you can adopt and help us with and make it better, right? So let's go through some of the kinds of search. So the first of these is lexical search. We're all familiar, this is the one-shot model. This is where I type a bunch of stuff. And the idea here is if I want to have some gaming headset with a microphone, I should take those words, I should match them to the products that I have, both the titles and the descriptions, in order to retrieve. This particular one, I think this is kind of funny. We're using the Amazon product Q&A data set, And this particular one is an example of how people who make products spam search engines by throwing in the same term millions of times to increase the retrieval, right? So this is a gaming headset with a microphone, but you can see gaming headset, microphone, right? So the idea with lexical search, and all of search is really about finding something in the catalog of things that you know about, the search engine knows about, that are similar to the thing that the user is presenting as a query. There's this inherent notion of more or less similar that drives what is the right or what is the search result that you get. For the lexical world, words are really the units of meaning and similarity, right? So you can go from the very concrete, so soul, our son, is a very concrete word. You can go all the way out to very abstract words like love that are sort of internally referential and very hard to define precisely. But the words are the things that actually carry the meaning and are what we are trying to create the similarity for. So the search query then expresses the intent of the user through the words, and the words capture the meaning of that query. And for lexical search, the idea is, okay, well, if we match words, we'll match meaning, and we'll create similarity. So the more matches, the better. The more rare the terms matched, the better. That's how we decide for lexical search what is a relevant search result. For vector search, we take all of our stuff, we run it through a large language model that creates a vector embedding. Now, vector embedding similarly captures the meaning of the words, but in a way that is learned and that is more contextual. We're breaking out of that boundary of the single word into the vector space. And then, of course, when you query, you do the same thing. You have an information goal. You run your query through a vector embedding model. That puts it into the same semantic space. And then you retrieve the stuff, hopefully, that matches your query. So what does this look like? If you've never seen one, probably you have. This is a small portion of a 1,536 dimension vector. This codes the meaning of a piece of text, and it enables matching within a vector space. So when we talk about similarity, and when we do search, we take the query, we embed it into that same vector space, and I'm showing here a visualization of the vector space that has about 20,000 data points. You can see stuff kind of clustering together, right? So stuff that's similar is kind of clustering together. We project our query into this space, and we decide similarity based on proximity. So that cluster of objects on the bottom left is similar because it's close, and the one in the top right, not similar, it's far, far away, right? So this is our notion of similarity for vector search. We talked about sparse coding, and sparse models take the full set of words and use a tokenizer to reduce it to about 32,000. We then use a transformer to generate weights for each of these 32,000 tokens. So the representation looks a lot like this, where if I have Apple products are expensive, you can see I have higher weights for things like Apple and expensive, chip, store, etc. And other weights are lower, like in this case, no, we don't have food. Okay, so look at 2, and you can see an apple a day keeps the doctor away. We get higher weights on apples and doctors and medical and prevent and fruit and diet, right? So again, this is a 2-step kind of process. We tokenize, we reduce the overall number of vectors. We then are able to use transformers to provide weights. Most of the weights are 0. These don't look like dense vectors. When we're doing similarity then, we take the query, similarly create this vector for it. So in this case, Apple, gift, something phone, electronics, something phones. Those are pseudo tokens that are created by the tokenizer. And then we're able to do distance by using a dot product. So sparse vectors have some of the flavor of lexical, some of the flavor of dense vectors, but enable more efficient matching, faster matching, and bring some kind of hybrid flavor to the matching that you're doing. OpenSearch project has actually AWS, open sourced, a couple of sparse models, and you can run in a couple of different modes. So you can only encode documents, or you can encode documents and queries. If you only encode documents on the bottom, you encode your documents, and then you use the tokenizer to do the query tokenization and the matching. And finally, we have our conversational search, which, again, Eric brought this up, where users are coming really with more questions. We do a retrieval for relevant context that we can add to the prompt that we send to the generative LLM. The LLM comes back with a response. Part of the context that we send includes not only search results, but also the history of the conversation. In this way, we break out of that one-shot matching strategy. So we're able to say, get me some shoes for the beach. Shoes come back. They're all women's shoes. I can just type, I am a man. And the conversational context helps, and then I get men's shoes back. Oop, wrong way. All right, so all of this stuff is really cool. Probably all of you had heard all of that stuff before. Maybe you're even working with this stuff. When you're working with it in OpenSearch, there are a couple of key pieces and a couple of key ways that you work with these different models and different paradigms of searching. And the primary one is the neural plugin. The neural plugin provides the connection between OpenSearch and the model. Now, models can be remote, hosted on a third party. They can be local, hosted on an ML node in the OpenSearch cluster. But in either case, the neural plugin is how you connect to and use that model to generate, for ingest, embeddings. Documents come through. You define an ingest pipeline. That ingest pipeline refers to a model via a model ID, and it automates the process. You also provide a field map so that you know that this is the source text field, this is the destination vector field. You provide that map. The neural plugin does the call to the LLM and places the embedding into the document. If you're using a third-party model, remote model, you have a connector framework that enables you to define a connection to a remote service, including authentication, the invocation methodology, post-processing, and tell OpenSearch how to talk to that external model. On the search side, very similar. Query comes in. OpenSearch has a number of different processors that handle calling out for embeddings, that handle calling out to re-rankers, that handle doing all of the work of bringing the embedding in and matching the embedding, right? So hybrid queries fall in there as well. So you have these OpenSearch pipelines on both sides of OpenSearch. When you use all these methodologies, you'll be using pipelines, connectors, models by model ID. So on the indexing side, again, just peeling back one layer, you have your raw data coming in, you have some documents, maybe you have some images. You're going to use the ingest pipeline. There are a number of processors. There's the text embedding processor, which generates a text embedding and places it into a destination field. You have your multimodal search, where you can have a multimodal model, takes an image, takes text. You'll use the multimodal, the text image embedding processor. You have the sparse models. You'll use the sparse encoding processor. This is how you engage and bring the data in with the appropriate vector stuff. So these processors, again, bring the embeddings in, and you send them off to the OpenSearch index. On the query side, again, you have the neural plugin. You have neural search that does the embedding for the query and runs a KNN query with that. You have the neural sparse processor. This, again, does the sparse embedding and provides you that query. And you have the hybrid processor that enables you to run both lexical and vector. In between, it's calling out maybe through the connector, maybe local model to create those embeddings. Ultimately, you query against the index, and you get your ranked set of documents back. So a couple of quick examples. On the mapping side, they all worked very similarly. So this is one of the reasons that we brought this library. They all work very similarly. So I have a couple of examples, but honestly, they mostly look like this, right? So you have an index mapping. You have a vector embedding field. It's type KNN vector. And then you have your image binary. You have your image description. Those are your text fields. On your pipeline, you're going to use the text image embedding in this case and provide that field map that says take the embedding for the text description, put it into the image description. That's where the vector goes. The image itself goes, the vector goes in the image binary, right? On the search side, again, you'll have a pipeline. This is a hybrid pipeline, and it engages processors. In this case, it's the normalization processor that blends the lexical and vector search. You run your query against that pipeline. For a hybrid query, again, you just give it 2 different queries. Hybrid actually, as a query type, takes up to 5 clauses, and they don't all have to be, none of them could be vector. So hybrid is actually a way that you can blend multiple different queries, whether they're vector or lexical, using the normalization, whether it's RRF, reciprocal rank fusion, or this min-maxing, this kind of combination. As I've been saying throughout, these are all very similar. Like the way they look in code, I create a pipeline, I create a connector, I create a model, I deploy a model. All of these steps are similar regardless of which methodology you're trying to use. And I diagram them there. You need a connector, you need a model group. Model group provides access control for models. You need to register the model, you need to deploy the model, you need to create a pipeline, you need to ingest your data, you need to create a search pipeline, and then, of course, you can search your data, right? So all of these steps are kind of repeated code and a bit error-prone. So we decided to come up with something that's simplified. So just to peel back the layer a little bit, OpenSearch is a distributed system, as we all know, a number of different nodes, and within those we have coordinator nodes. These coordinate processing requests. We have data nodes that actually process requests, cluster managers that keep the cluster together as a cluster, and we have ML nodes that do ML processing. So when you create connectors, really you're working with those either ML nodes or data nodes to connect out to various systems. Quick example, just so you can see a connector. Main things here, again, we have credentialing, we have actions, and this is what happens. This is where the model gets invoked. You deploy this thing in OpenSearch, and it gives you a model ID. Models are the generic way that we refer to any model, right? So you can have local models that are running on an ML node in the cluster. You can have remote models that are running remotely via a connector. I wanted to mention we have integrations in Amazon OpenSearch Service that make setting up models in SageMaker and Bedrock easy, sparse and dense. But really to the point of the talk, we open sourced a library that helps you with all of this deployment and management of the pieces in OpenSearch. And so Yuye is going to come and demo and show you that code base.
Thank you, John. And now we know that to use the vector search feature in the OpenSearch, you need to configure a connector, a model, a search processor, and an ingestion processor. This may be a little bit complicated for the beginners to the OpenSearch, so that's why we built this repo, OpenSearch ML quickstart. If you are interested in this repo, feel free to scan the QR code here. Next, I will briefly walk through some typical classes in this repo. For models, we have both local models and remote ML models. For local ML models, we are going to download that model into the OpenSearch cluster. And for remote ML model, the model is actually hosted on a remote service. It can be either Bedrock or SageMaker. To use a remote model, we are going to use the connectors. As you can see here, for the ML connector class, we have two sets of them. The first one is OSML connector, and the second one is AOSML connector. Here, we have two sets of them because the credential between OSML connector and AOSML connector is different. Here, OS and AOS stands for Open Source OpenSearch and Amazon OpenSearch Service. For Open Source OpenSearch, the credential is actually a pair of access key and secret key so that you can have access to the Bedrock or SageMaker model. For Amazon OpenSearch Service, the credential is actually a resource identifier, namely the ARN of the resource you are looking for. It can be either the ARN of the Bedrock model or a SageMaker endpoint. John has mentioned that we are going to support conversational search, so this part is done by LLM. So we are going to have another connector named is AOS LLM connector, so that we can have access to the large language models. The OpenSearch ML Quickstart repo works on the Amazon PQA dataset. This dataset stands for Amazon Product Question and Answering. It contains millions of products and dozens of categories. If you are interested in that, it is a public dataset. Luckily, you can scan the QR code to get the details. On the right-hand side of the slides, you can see there is a piece of sample data. As you can see there, you can see the item name, the product description, the question text, and also the answer to the question. The OpenSearch ML Quickstart is working on the PQA dataset, and here is a paradigm of how we are going to use that dataset. As you can see here, for the first demo, we have a file named Q&A file reader. This file reader will read the dataset and do some pre-processed stuff, and finally ingest the pre-processed data into an OpenSearch index. And now it's time for demo. Okay, here is the search results. There is 3 items. And as you can see here, we have the first item, we have the gaming headset, and headphone, microphone. Second item, gaming headset, microphone, gaming headset, and microphone. So as you can see, the lexical query works well when you have some keywords to search, and the keywords is popular in the corpus. And now let's try with another search query. This time, the search query is earbuds protecting me from noise. Here is the search results. Unfortunately, lexical search does not work well in this kind of query. As you can see from the item query, we got costumes, and casual. It means that once we have an ambiguous query, we do not have keywords, so that we cannot use the lexical query. But how come that we retrieve these 3 results? let's take a look back into our search query. Earbuds protecting me from noise. As you can see here, none of the item has the keyword earbuds, none of them has noise, none of them has protect, but it actually has the keywords me. There is multiple me in the item results. And another word is from. There is multiple from in the search results. That's not actually what we want for the lexical search. Instead, we want to capture the semantic meanings. So that's why we're going to have the dense search. Okay, I'm going to share the slides, sorry for that. For the dense vector here in this example, we are going to have a SageMaker model. The model name is MS Markov Distilled Bird Task B. And here we are going to briefly show you with the current code of the repo and how we are going to use this repo to show you. As you can see here, this is the script I'm going to run, and I'm going to declare the type of the host to be AOS, which means Amazon OpenSearch service. The model type is the SageMaker, and the embedding type, it is a dense vector. Besides, we need to specify the name of the index, the name of the ingestion pipeline. Given these configs, we are going to obtain an instance of an ML model within this function, which is getMLModel. Remember that we have host type to be AOS and model type to be SageMaker. And this time we are going to retrieve an instance of AOS SageMaker ML connector. Given this ML connector instance, we are going to instantiate an instance of the remote ML model. So this is exactly what the model we are going to use for the dense search. Now, let's take a step back and look into what's happening inside the AOS SageMaker ML connector. You can see here the first function, it means the inline policy. It means that for this policy, you are going to grant with a role with the permission to invoke a SageMaker endpoint. Here, you are going to specify the resource. It can be the resource of a sparse model or a dense model. The sixth function here, it is very straightforward. It is going to return a file name. This time, the file name is SageMaker Dense. Here is the template of this file. As you can see here, the service name is SageMaker. You are going to fill in the region later. From the actions, you are going to specify the URL. Now, given the file name, this class is going to create a connector with this payload in this function. Okay, that's a walkthrough of the code, and now it's time to try with this query. Now, we are going to try with the same query, earbuds protecting me from noise. As you can see from the search query here, we are going to have a actually neural query instead of a match query. And the field we are searching for is the embedding field instead of the text field. This time we got the chunk embedding. This is the query text, and besides the query text, we are going to have a model ID here. This should be exactly the same model we are going to use during the ingestion. Okay, let's check the search results. From the item category, you can see the earbud headphones is correct. The second item is also correct. It mentions about hearing protection and harmful noise. For the third item, it mentions hearing protection and harmful noise. It seems that lexical search does not perform well on this ambiguous but dense search can solve them. So what if there comes another query? This query is earbuds supporting Bluetooth 5.0. Here is the search results. The first item name is correct, but it does not have too much useful information. And the second item name, it contains Bluetooth, it contains 5.0. But unfortunately, the 5.0 is not mentioning the version of Bluetooth, so it may be not a correct example. The third item is correct. So although the dense search can capture to some extent, capture some semantic meaning, but once we have keyword and dense search may not perfectly work as a balance between the keyword search and the semantic meaning search. Luckily, we can have this sparse search. In this sparse search example, we are going to have a sparse model also on SageMaker. This time, the model name is OpenSearch Neural Sparse Encoding V1. Now, let's go to the demo. For the sparse search, let's try with the same query. Earbuds protecting me from noise. This time, the query is neural sparse instead of the neural. As you can see, it can capture the semantic meaning of hearing protection and harmful noise. Now let's try another query. Earbuds supporting Bluetooth 5.0. From the search results, as you can see there, it mentions Bluetooth 5.0 for the first item. The second item also mentions the Bluetooth 5.0. And also for the third item, Bluetooth 5.0. So, as you can see, the sparse query can work perfectly on this search query. Now, as we currently mentioned, we have lexical search, dense search, and sparse search. So we have hybrid search to blend those queries together, and so that you can have the benefits of all these queries. In this example, we are going to do a hybrid search of both a sparse model and a dense model. Okay, so now let's try with the hybrid search example. This time, the query text is earbuds supporting Bluetooth 5.0. Here is the search query of the hybrid query. As you can see, the hybrid query contains an array of queries. In this example, we are going to use both a sparse query and a dense query. Here is the dense query. It is searching for the dense embedding field. The sparse query is search for the embedding field of the sparse features. The query tags, they are the same, but the model ID is different. Besides the search query, we have the search pipeline config. The search pipeline is a normalization processor. It normalizes the score of both the dense search and sparse search. The technique is minimax. After the normalization, it combines the score with arithmetic mean. This time, both the sparse search and dense search is going to have equal contribution of the hybrid score. Now let's check the search results. As you can see, the first item is from the previous dense search. Both the second and the third items comes from the dense sparse search. Now it's all about the search. It's time for the conversational demo. Suppose that I am a user coming to the Amazon website. I do not only want to search, instead I have a question. So what if my question can be answered by a large language model? So we are going to do it in a RAG manner, which is retrieval augmented generation. In the first step, we are going to use a SageMaker model to retrieve the results, and after that, we are going to use an LLM to ask it to summarize the results and then answer the user's question. Okay, let's demo. This time, suppose that my question is, what sheets should I buy if I have a cat? Here is the search query. From the first part, it is actually a neural sparse query. From the second part, it is a query extension. It mentions that the model type of the LLM is Barrel Cloud, and the question of the LLM is the same as the query text. Here is the search results. Let's check the question. The question says that I want to buy this, but I'm worried my cats will rip the cover. And the second question is, how are these sheets for holding on to pet here? The third question is, I want this to cover our box springs, but we have cats. It seems that all three questions are relevant to the query. Let's check the answer from the LLM. From the LLM answer, it seems that based on the search result, smooth materials like satin or microfiber sheets. It also pinpoints some specific name of the product. As you can see, it is actually the second product. So it can answer the user's question and recommend a product. Thanks. That's all part of my demo.
Thanks, Yuye. So just a quick wrap. Chat, semantic search, vector embeddings, they provide new ways of retrieving and interacting with your data. OpenSearch provides the tools, but there's still a lot of work and repeated code that goes into setting up the connectors, setting up the models, managing the connections, doing all of that stuff. So OpenSearch ML Quickstart, again, is all of these examples are from the Quickstart repo. There, you can download it, you can run them all yourselves. And they'll serve both as an example, but then hopefully a reusable example that you can bring to your own code and your own search applications. So thanks very much. Really appreciate it.